we're a little bit already behind the time, and we Germans, we like our schedule, so I just go ahead and start. So first of all, thank you, all of you, for being here today, and that I can give this final presentation to you. Thank you especially to the City of Duluth and to UMD making this exchange possible, and to the Climate Smart Municipalities program, with which I got the opportunity to spend some time here in the United States. So my name is Max Schüssler. I am a mechanical engineering student from the University of Siegen in Germany, and I spent the last 10 weeks here in Duluth, with the properties and facilities management, working on this project to figure out a hybrid energy system for the Lakewood water treatment plant. And this is all, how I said, with the Climate Smart program, where 5 German cities from North Rhine-Westphalia partner up with 5 Minnesotan cities to work on renewable energy and sustainability questions that concern the municipalities. And as Duluth is the partner city of Siegen and they both have universities, they said, well, we could also do some kind of academic exchange. And so I got to be the first one who tries this somehow, in some way, how this is possible and how this works out, and spend some time here with the city, but also in close collaboration with UMD and under academic supervision from Professor Hoxie. And so I just jump right in, and I have 4 points I want to go over in the next, I don't know, maybe 45 minutes, and then we'll have plenty of room to discuss questions that might occur. If you have questions in the meantime, just go ahead and ask right away. If you don't want to wait till the end, or it might be just a good thing for everybody else in the room to know, just ask right away. So first of all, I want to talk a little bit about the project outline and what I started up with. And so first of all, what are the problems the city faces and what they want to tackle right now? And it came last year in 2016 after a windstorm to a big power outage, and the city was 1 hour short of running out of water for every part of the city. So the first problem is a resilience problem with the water distribution system right now, that it might be a good idea to look into a new backup system for more resilient electricity supply at the Lakewood plant. Secondly, the energy costs are really important. The City of Duluth spends around 50% of the whole electricity bill just for pumping water around the city, which means they also have, of course, a great interest in reducing those costs. Third of all, concerns the energy plan of the City of Duluth, that they want to reduce 80% of their greenhouse gas emissions by 2050 compared to a standard of 2008. And when I capture this now in a set of goals, a hybrid energy system, so a combination of backup generator, renewable energies, and some kind of storage, would tackle all those problems in a way that I could make the water supply hopefully more resilient, that I could cut the usage charge I have, so the kilowatt hours of energy I use, that I could even cut my demand charge when I have a battery, that I can really peak shave something. And fourth, that I really can reduce my greenhouse gas emissions and come a step closer to the set goal for 2050. And first of all, for engineers, everything is just a gray box in the beginning usually. And so I picture also for this hybrid energy system just a gray and big box. And besides that, I have a grid connection. And those two together are supposed to run my pump house and water treatment center down at Lakewood. So these are 2 separate entities, but they're all, when I talk about the Lakewood plant, I usually mean both houses together and what electricity they both together consume. And in the hybrid energy system, I have a generator, I have renewable energies, and I have storage. And I divided for this first part into 2 different kinds of storage, in the long-term and in the short-term storage. I did this because I could think, when this is my electricity flow on a daily basis, and this would be my emergency electricity flow, so to say, that my long-term storage could serve my resilience goal. Because maybe it might be possible for my generator to have a smaller size, and I could use my battery or my energy storage to cover the surge load of the pumps or whatever is in the Lakewood plant, and cut my costs by just installing a smaller generator. And with the short-term storage and with the renewable energies, I really want to focus on the cost goal, to reduce somehow for the city the costs that occur due to electricity use for the water. And then there are many options I can choose from. And then I just have a set for each little component of my hybrid system. I came up with a set of options that I can choose from to make a good total system out of it. And there would be diesel and natural gas for the generator. There would be a photovoltaic system. I will abbreviate this always as PV on those slides here, so it's always solar energy. And for the long-term storage, I can look into air compression, hydrogen, maybe additional reservoirs I can place within the city or increase the fill height of the existing reservoirs around the city. For the short-term storage, I can look into batteries, so the really chemical solid-state batteries, or I might even look into a pumped hydro scenario. Maybe this is an option. So this is where I started off with to see, okay, I have all those options, what can I really have? What kind of arguments could I make for which component here? And then once I figured out all those little parts and hopefully come to a conclusion for each big box here, what option is the best, I want to optimize this system and somehow figure out a pumping schedule for the water treatment center right now to use as much of my hybrid energy system as possible. And then this is my project right now, so the scope 1, how I call it, and maybe if that's a solution that is appropriate for the Lakewood plant, maybe smaller applications of that system can be just downscaled and also be installed at all the other pumping stations around the city. Just to give you an impression on what I've been working on, I said it's 10 weeks. Those are just my 10 weeks I've spent here, and these are just the topics I mentioned and what I worked myself through. And this is the way I've come now, and we are now in the final week. And so this is my final presentation, of course. So hopefully somehow a result, what concept I came up with. Now I want to back up one step again and talk about some really, probably most of you know that, some basics that I will mention in the course of this presentation quite often. And this is for one energy and for the other it's power. And just to go over this, the kilowatt hour, it has the watt, which is joule per second, but again multiplied by some time again, so it is again just a unit of energy. And when I refer to energy, I usually say it's the usage of the power plant out there, and it's usually the measurement is kilowatt hours. And the other is the power. This is my joule per second, so my rating of my energy per time. And this is usually demonstrated in the peak demand, so the maximum kilowatt the treatment center wants to pull from the grid per time frame. So that's the power rating. And to illustrate this really easily, this is my little battery. And if I charge my battery in this rate, I can see that the amount of energy I can store in this is just indicated by the amount of green bars I have in this battery. And the speed with which I charge that battery up, this is the power of the battery, the charge or the discharge rate. So just as an example, if I double my energy, I just double the size of it, but I don't increase the speed of charge or discharge. On the other hand, if I increase the speed, I increase the power, but I let the energy stay the same. Just because this comes up quite often, I just hope that this slides help me a little bit. And now I talked already about the electricity flow of the system, but now it's also really important, what does the setup really look like? And it all starts somewhere at the lake, because we want to have water taken from the lake and supplied to the whole city and all households and all consumers. And we have our Lakewood plant, which is a box made of two boxes again. So the pump house on the one side and the treatment center, where all the filtering and all the chemicals and all this is happening, is right here. And the pump house where actually the pumps are situated is right on the other side. And I have my reservoirs that are all distributed all around the city. And the city has basically 3 major levels, which are around about 900 feet, and those are higher elevations, but the main body of water is stored at that first level, at the first reservoir height, and this is around about 50 million gallons we can store in this first level, and the total system can hold up to 67 million gallons. And in the pump house, how I said, we have 3 different sets. And the city decided that they call them pump 1, pump 2, and pump 4. So don't get confused, there is no pump 3 in this scenario, it's just the way how it's set up. And the pump 1 has a high and a low lift pump. This is because the water flow is like this, that the lake gets pumped by the low lift pump, the water into the treatment center, then it flows back by gravity to the high lift pumps, and the high lift pumps pump the water up to the first reservoir level. And what happens right now is that one set is always activated at a time, turned on at a time, and the other two are always off. So it's really a manual switch. They push when they want to decide we want to pump 60 million gallons a day with pumps 1, around 20 million gallons a day with pump 2, or 30 million gallon a day with the pump 4s. The pump 4 is really just there as a backup plan right now. It's just run once a year to see if the pump is still functional. The city doesn't need it right now, but it still is there, and it's functional in the case of another emergency of water shortage. And then from here on, there are other pumping stations, the smaller pumping stations, where the water is just pumped up to the higher levels of reservoirs, where then again it's a gravity-fed system back to the household. So this is the whole setup I'm talking about the whole time, and this is the Lakewood plant with the pumps, which is the main load of the whole Lakewood plant. Yeah. So this is my setup. This is what I face right now, and from now on, when the pumps and how they operate right now, this is for me set. So I didn't look into what would happen if we would change the pumps. So the pumps are, first of all, this is just a whole other topic, set in place, because this determines a lot about my load character we have down there, and I just go from there saying, okay, what if we install a hybrid energy system with the existing equipment of the pumps we have at the Lakewood plant. And now I got into the components, and I just looked through each component, generator, then the renewables, and then the storage side, and what is the best option for which. And for the generator, it tackles the resilience goal of my whole hybrid energy system. So I need to know what load do I actually have to back up. And after talking to the engineering office here, they said, okay, we actually only need the pumps 1, the high and the low lift pump 1 to run at a time, because we could have measures that the city is prohibited to use too much water, that they all know it, and it should be sufficient in an emergency case to run the pumps 1, which leads to 900 kW of constant load. And the worst outage the city has seen so far is 12 hours. And so I said, okay, I'll look for a scenario where I can back up the system 24 hours and which sizes of generator I need for that. And then the options were natural gas and diesel generator, and those are two really different things to look into, because the diesel has a higher energy density as the liquid, which means that when I need to supply torque to really start my pumps, I need less rated power for that diesel generator. On the other hand, natural gas has a lower power density in the liquid itself, which means that it can supply less torque at the same power rating as the diesel generator, which means my natural gas generator has to be quite larger from the rated power that I install than the diesel generator. This is how I came up with, or a preliminary study done by MSA from the Twin Cities, that we need 1.8 megawatt of power for a diesel generator or 4.5 megawatt for a natural gas generator. And what this boils down to is that our total cost for the diesel generator sums up to 2.2 million, and for the natural gas generator, or genset, we have $6.5 million, which means that the diesel generator option for such a huge load as the Lakewood plant is just the most feasible solution out there. This might change if we are looking at loads that are way smaller. Then natural gas might be an interesting solution, because on smaller scales, natural gas is usually cheaper than diesel generators. Second component, I looked into the renewables. And I first thought maybe there are other options than photovoltaic even. And I looked, okay, maybe wind energy, which is usually a great idea, but here in Duluth, as a point at the tip of Lake Superior where there is a main bird migration path, it's not a good option to install wind turbines here for renewable energies. Maybe geothermal energy. The problem with that is that the capital expenditures or the front-end costs for a geothermal plant are just too big. And we are looking at a system which is commercial industrial scale, so it's the medium range of sizes, so to say. It is way bigger than residential PV, for example, on house roofs, but it's also a lot smaller than grid scale applications, which would be probably a geothermal plant. So this is why I ended up with photovoltaic to look into further. And this is the area we have at the Lakewood plant available, and these are now spaces that might be possible for PV applications. And actually this yellow space right here, this was a space also a student group last year from Professor Hawks' sustainability class looked into and looked, okay, what is the capacity of PV we would be able to install there? But I said, well, we also have some space behind the plant and also on that cap, they had it also. And I end up with a total of 50,000 square meters, so this is around about 12.5 acres. And then I looked into comparable PV setups that are here in this area, and there's the Black Bear Casino, and with that 1 megawatt PV installation. And I looked how much PV they have installed per ground, so per acre, so to say. And I took this as an optimistic estimate for the Lakewood plant, and I ended up with around about 2 megawatt DC installed capacity. But again, we have really interesting shapes here at the Lakewood plant, which means we will have some losses on the edges and all around. So I said, okay, our ground cover ratio will be definitely worse. And so a good estimate, what I came up with is a 1.5 megawatt system, which should be installable on that ground around the Lakewood plant. Now, since we have already what power we have, the next question is, okay, but how is the solar radiance here? And for that, I have data from NASA and from PV Watts and compared them for both setups for the 1.5 megawatt system and for the 2 megawatt system. And for the 2 megawatt system, PV Watts and NASA have a good agreement, and also for the 1.5 megawatt system, they align quite well. And so I estimate that we could harvest up to 2 terawatt hours of photovoltaic energy down at the Lakewood plant. I put this into relation later, how this compares to the actual energy consumption we have at the Lakewood plant. And this is just the summary of my PV analysis, maybe an interesting number for people who are also studying PV in this area that I came up with. 1.3 megawatt hours per kilowatt per year, or 1,277 kilowatt hours per kilowatt a year that I can harvest with the installed capacity that we have up here. And I have an estimated cost of $2.8 million for the 1.5 megawatt system and $3.7 million for the 2 megawatt system. And those numbers are based on the newest numbers from the NREL and their quarterly numbers on their PV prices right now. And this is just an overview of what we could actually produce down there. And how I said already, I think that the 1.5 megawatt system as a conservative estimate is, first of all, the estimate I will go with to see on the lower end where I end up with the 1.5 megawatt. After renewables, now I said, okay, let's look at the storage side. And I not only looked into electricity storage, but there are also I could use a water reservoir to just use my energy to store it right away in potential energy. So this is a broader term. And I looked into those options right here. And the first 4 options, the lithium ion, the lead acid, the nickel metal hydride, and the nickel cadmium, those are all for solid state chemical batteries. Those are for long on the market. Lithium ion, probably everybody has one in their smartphone in their pocket right now. And they have been many years on the market and are well established. Another technology I looked into was the vanadium redox flow battery. So this is not solid state, how the name flow already indicates. So it's another setup. I'll explain this later in more detail. Then 3 other options are maybe also compressed air. What compressed air storage does is it takes excess energy or electricity I have and compresses with a turbine my air and stores this air in pressure tanks. When I compress my air, I have really a lot of heat I also need to do something with. And so I have 2 options with the heat. I can just have it as excess heat and don't use it anymore, or I try to have a heat storage in some kind. When I need electricity again, I release my air again through a turbine and generate electricity. The problem is when I expand the air, the air will cool down. So I need to resupply heat. And if I'm able to resupply the heat that I took out in the compression process, I might have even an adiabatic process. This is the field of study those people look into right now to create an adiabatic compressed air energy storage, which then would have really high efficiencies. The problem is that this adiabatic process is not possible right now, which means when I compress my air, I have the heat and I can't do anything with it, so it's waste heat. And when I expand my air again, I have to resupply heat, and I usually do it by droplets of natural gas and ignite them in there to resupply the heat, which leads to really low round-trip efficiencies, why this option is not a good option for my scenario. For hydrogen, many people looked also into that, if it's a good possibility for energy storage. And it might be a good option if I can use my hydrogen to apply to my natural gas grid, or use it as a fuel for cars or other applications. But also when I reconvert it to electricity, the round-trip AC to AC efficiency is really low. And for the last, for the pumped hydro, which is that I use my electricity to pump water up somewhere to a reservoir up the hill, and when I need electricity, I release the water and generate again with a turbine my electricity. But again, we're looking about a scenario for the water treatment center or water treatment plant, so the whole goal is to pump water up the hill and not release water down the hill to pump it somewhere else up, which means the pumped hydro is, for the use case of a water treatment center and supply infrastructure, not a good option. And this is the flow battery, because this is the newest technology. Maybe some of you are unfamiliar with it. I try to just cover it really quickly. This here in the middle is the cell. This is just a regular battery cell, looks almost alike, just like this. The addition a flow battery has compared to a solid state battery is that I have my electrolytes, which are usually in the cell, externally stored. And one is on another charge level than the other electrolyte. In the case of the vanadium flow battery, the electrolyte that is used is of course vanadium, but at 2 different charges. Which means if I pump it through the cell, it will get rid of one electron which tries to get through a metal conductor somehow, and the ions will go through a membrane into the other electrolyte. And they can recombine here, and since I can pump this electrolyte in this circle and can pump this electrolyte in this circle, depending on the size of my energy storages or my electrolyte storages, I can scale the energy supply of my battery just as I want it to be. The same goes for the cell in the middle. If I just have a second cell and my storage tanks stay the same, I can really easily increase the power that this battery supplies, which has the great advantage over all the solid state batteries that I can scale my power rating and my energy rating independently with this battery. So this is not possible with the other technologies right now. Okay, so is it usable? I said already the last 3, no. They are just not feasible for the scenario I look into. Either the costs are too high or the efficiencies are too low. The second point is the technology up to date? Is it used right now? Do people still invest in this technology? And what it comes down to, that the 3 solid-state batteries in the middle are not a good option anymore because they are outruled by lithium-ion most of the times. Because lithium-ion has a really high energy density by cubic meter or by liter, so gravimetric density, which means that in applications where the weight really matters, in cars, in smartphones, or in those applications, lithium-ion outrules all the others, also by efficiency. But again, the vanadium redox flow battery, that's a really new technology, and it can compete on that scale, and is also up to date. And the third point is longevity and durability. With solid-state batteries, everybody probably experiences it, that the lithium-ion battery in the smartphone, over the course of years, somehow gets worse. The charge I had when I first started using my phone was way better than the charge I have after a couple of years. And this is just because the chemistry wears out in those cells, and I cannot recharge it to 100% that I used to have on day 1. This is not true for the vanadium flow battery, because the real energy is stored in the electrolyte tanks, and this is just a stable chemistry, which means it doesn't degrade over the course of years. I can always charge it up to 100% and discharge to 0% without any damage to the battery. And this is if I would cycle my lithium-ion battery from 0 to 100%, it would definitely get damaged. So I need to have a minimum charge in my lithium battery so I can just use more of my flow battery by rating capacity. Another advantage is that my my flow battery does not discharge itself. So when I do nothing with my flow battery, it just sits there. It doesn't do anything. And with the solid state batteries, they do always something. Either they are charging or discharging. If they are sitting around, they are discharging. Not so with the flow battery. So these are all advantages why I said, okay, maybe the flow battery technology is the one to look into and see if we find a good application down at the Lakewood plant with it. And here's a picture just to see what such a system would look like. These are 4 half shipping containers, and always 2 containers have the electrolyte for the vanadium 5+ charge, and the other one has the electrolyte stored for the vanadium 3+ charge. And the 5th container is the cell, so where everything is cycled through. Just to give you a proportion of what such a system would look like, this is 2 megawatt-hours and 600 kW of power. And now I looked into the technologies. I know what something like this could look like, but what do I actually need at the Lakewood plant? And so the next thing is the load character of the Lakewood plant. And this is the data we get from our utility, from Minnesota Power, what the grid actually sees, what we consume down there. And what you can see is that we have 3 distinct levels our Lakewood plant operates on. We have the 900 kW line, we have a 1500 kW line, and we have somehow a spike at 1800 kW roundabout. And how I mentioned already earlier, the pumps and how they are set up, this aligns quite well with which pump is running at which time, which is pulled from the system that the city uses right now. So this bar right here, the green indicates if pump 1 was running, the red pump 2 was running, or the purple is when pump 4 is running. So you can see that our load is majorly influenced just by the pumps and how they operate. And how much of the total load they actually have compared to the treatment center, so the whole water processing, you can see by this difference right here. The blue is actually what the pumps use and draw from the system at 2,300 volts. And the yellow is the total Minnesota Power sees, so this difference is only what the treatment center actually uses. And the rest of the blue is what the pumps use for electricity. And then I looked for the battery. Yeah, please.
One quick question. Are pumps 1 and 2 operating simultaneously when you say that they operate always separately?
Yes, they are separating. They are operating always separately. So are either running the 2 pump 1s, the 2 pump 2s, or the 2 pump 4s. And they really switch the one pair off and then turn the other on. Yeah.
What happened to pumps 3?
Ask the engineers. Ask the engineers from the city.
Jim, this is a precision.
100 years ago, before my time.
They just disappeared. Yeah, any further questions before I go on, maybe? I looked into, okay, now I know what I want, now I know what the load character looks like, and now I want to know which size do I actually need for that battery. And I can either look on the side what the PV system supplies to the battery, or what my pumps draw from the battery. So I have a draw or a supply side. And I just did some math, and hopefully some good math about it, and I came up that for the power rating of the battery, when we look at what the pumps actually need, we need 540 kW. And if we look at the supply, so what the PV system at a really sunny day when the pump 2 cannot run because all the reservoirs are filled up, I would at a maximum need 540 kW to make sure that I can offset all my PV energy and not just let it sit there or shut off the PV system. And the same goes for the energy. I looked at some numbers there and came up for the battery storage when I could look at the pumps that I would need around about 3.5 megawatt hours of storage. And when I look at the supply side from the PV, that already 1.5 megawatt of storage would be sufficient. But the problem is, okay, I need again one battery and not two batteries that come to my needs. So I looked really what is on the market, and I showed you already the picture of the UE Technologies battery, and it fits quite well that they have their uni system power rating at 600 kW and their energy rating at 2.2 megawatt hours, which I from then on took to take this battery, which is really on the market and we could actually install, and how we could operate it to get the most out of the system. Okay, now these were a lot of tiny little things in those components. Now I looked at the bigger picture and looked, okay, what happens if I combine now all those elements together? And for that, this is what we, in the course of 1 year in 2016, have as an energy use at the Lakewood plant, around about 600 kilowatt hours per month that we consume there. And my PV system, remember it's a 1.5 megawatt system, so it's not a really small PV system, but it's only contributing around about a quarter of the whole load we have down there. And this is now the annual basis, 8 million kilowatt hours of energy draw and 2 million kilowatt hours that we can produce down there and could offset. The annual charges, now what do we actually get charged for that? Round about $700,000 a year just for the Lakewood plant itself. And how does it separate when I look into, okay, what do we actually pay for the usage? What do we actually pay for the demand? And what is the rest of adjustments and riders? And when I looked into this, I came down to that the usage charge is the majority of my whole charge that we have if I compare it by percent. And then if I look which riders are driven by which influence. So some riders are dependent on the energy use, some are dependent on the demand, and some are fixed. And I made this adjustment for 2015, and it comes down to that 63%, 64% roundabout are dependent on my usage charge, and only 23% are dependent on my demand charge. Which means the bigger my PV system is, the more energy I can produce, the more I can offset off the energy costs we have right now. So the better my payback, the better the feasibility probably for that project. And then I combined everything already in 3 scenarios that I came up with. This is the picture I showed you already, the picture I started up with, and I said for the generator, probably the diesel generator is the best solution. And for the renewables, the photovoltaic system is definitely the way to go. And now in my first scenario, I looked into what would happen if I wouldn't use the storage. So in this case, I wouldn't have a hybrid scenario anymore, so I would have 2 separate circuits, 2 separate systems, just one for the resilience plan and one for the cost-cutting plan, so to say. In the second case, I looked into what would happen if I used my flow battery just to reduce the cost, but not to use it in an emergency case, because again, we have another technical device somehow in a resilience plan, and the more parts that can fail, the higher the likelihood something can fail. So for the scenario 2, I just use the flow battery to reduce the costs. And then in the third scenario, this is the real hybrid scenario because I use the battery with all what it actually can do for me, that I will also be able to downscale my generator and use that battery to operate in the case of a power outage. So my case 1, with the 2.5 megawatt diesel generator and the 1.5 megawatt of PV, this is the cost, the total cost I will have. So my capital costs, my front-end costs, I will probably have around about $5 million and an annual charge of $20,000. But on the savings side, we would offset our 2 million kilowatt hours and probably be able to peak shave by around about 400 kW, which in the end comes down to an 18-year payback period if we don't somehow net meter anything with Minnesota Power, which means that we do not use our excess energy to net meter it. So sell it back to Minnesota Power, that's not the right term for it, but to net it out. And then if we would do this, if we had this agreements that we don't have excess energy at all, the payback period would be down to 17 years. For my scenario 2, so just the flow battery for the cost-cutting scenario, and the 2.2 megawatt hour system from UET and the 600 kW power rating, we would have around about $6 million of costs and $30,000 a year. And this would also boil down to probably of an 18-year payback period. What I have to say to the payback period, also for the scenario 1, this is calculated without the generator, because the generator only tackles the resilience goal. And on something that makes my system safer, there is no payback on this. So I'm just using the components I also use for cost cutting, because I can actually calculate something on that. And now my third scenario, I actually use my battery in a whole hybrid way to its maximum extent, hopefully. And I would have only $5.4 million of investment front end, which is lower than scenario 2, because I can downscale my generator to 1.8 megawatt instead of my 2.5 megawatt, because I can use the power of my battery to offset some of the surge load I have to cover when my pumps start turning. And then my savings, I have also that I'll be able to offset all my energy, peak shave down to 750 kW, that we don't have to pay for as a peak demand per month, and this would also lead to 18 years of payback. Now this is my summary page, so this is the 3 scenarios I looked into in the end, and you can see that, again, all have a similar payback period, just the front end capital expenditures are different, and that the third system is the actual hybrid energy system. And of course, my task was to look into a hybrid energy system. It is an innovative system, it has the flow battery in it. The cost of flow batteries will probably even decrease once we look into this more deeply, then it will become maybe even cheaper to invest in something like this. And 18 years for a renewable energy problem that is meant for a water treatment center where the electricity rates right now from the utility are really low. This has to be mentioned all the time, which of course increased my payback period, which means that my option 3 is hopefully the one that future students, future investigations will be done in. Now a quick conclusion and outlook. So when I answer a few questions, of course, many other questions arise, and this is also what happened here. And on the technical sides, things that should be addressed in the future is really looking more in depth in the flow battery technology. I had the 10 weeks for this, but this was definitely not enough time to capture all positive sides and also some disadvantages of the flow batteries. There are some concerns with the maintenance maybe of the membrane in the cell, but maybe there are also just other advantages I am not aware of yet. The second point is it really an option to add water reservoirs in the city? Is it really possible to cycle our reservoirs level higher to directly at high solar output times use the excess energy to start our big pumps to move as much water as possible? This is also something where more research has to be done. The third point is the inverter and transformer issue. So we have different voltage levels down there. The grid voltage is around about 4,000 volts. Our pumps operate in 2,300 volts. Our PV system would run probably at 1,500 volts. And so how does my AC-DC conversion and all my ups and downs in the voltages really translate in terms of efficiencies? That's also a topic that needs to be probably addressed if there are major concerns that might arise. And on the financial side, maybe it's an option that the backup generator is not owned by the city, maybe by the utility, by Minnesota Power, and run for their purposes for grid stabilization, and that we could use it as the city for our resilience backup plan. These are just options for the future that might develop. What were my goals? These are just my goals I mentioned really far back in the beginning. And I hope that with the system, the option number 3, I am able to tackle all those 4 goals right away. So this is why I'm, of course, a big proponent of this hybrid energy system. And I'm just left to say thank you for your attention.